things the IRDG over the years is getting some of the greats of infrared and Raman have spoken at this meeting, and it gives great pleasure to introduce Peter Griffiths, who's spoken at the IDAC. I was trying to bring it up many times. I don't know, is this the first time at the Christmas meeting?
First Christmas meeting. Third IRDG.
There you go. Peter needs no introduction. We are recording. We are recording. Hopefully, Peter will give us a great talk on the early days of FTIR. Peter.
I would like to thank Mike particularly for carving this statement on the top of the board. Remember the days of old, consider the years of each generation. In this particular case, this is quite some relevance to the talk that I'm going to give. So what Mike asked me to do was to talk about the early days of FTIR, typically up to about 1970, maybe 1971. And I'll show you the reason for the title in just a bit. So, really there were three fundamentally different types of Fourier transform spectrometer in the early days in the 60s. There were somewhat middle resolution, 1 reciprocal centimeter resolution, slow scanning interferometers for far infrared. They were largely developed originally at NPL and a few other places. There were the very high resolution near infrared spectrometers developed in France by Pierre Tom's group, and very low resolution rapid scanning interferometers for mid and near infrared. That were really the forerunners of today's instruments. So let me just concentrate first of all on the first type of instrument in this list, the mid-resolution, slow and occasionally step scanning in the instruments. They were, let's see if I'm, they were largely based on the NPL instruments developed by Alistair Gevy's group, who had postdoced with John Strong at Johns Hopkins University in Baltimore, Maryland, and developed a really strong group of far infrared people who published well over 100 papers in far infrared spectrometry with these instruments. I'll show you a few of these, but the first commercial instrument was put out by Research and Industrial Instruments Company, who was ultimately taken over by Beckman. RIC was based in Kent, as I recall. There was another instrument which was much more homemade, yet still commercialized, put out by Grub Parsons. There was an interesting character who worked for RISC. I won't give a name, but he worked for RISC for some time, then switched to Cadet, Société Cadet in France, and they came out with a far infrared instrument. And lo and behold, he switched to Polytech in Germany, and they came out with a far infrared instrument. Pure coincidence. All of these instruments were based on beam splitters which were Mylar, but there were a few other instruments as well. There were lamellar grading instruments. I'll show a picture of one of these that was developed in Strong's lab in the US. Polarization interferometers, which have a short but useful life. They generally used high-pressure mercury lamps as sources, which have somewhat better emission in the far infrared than, say, glow bars. and much better than Nernst gauze. The detectors, which I'll also show in a little bit, were typically Golay detectors which, thank goodness, are never used anymore. The laughter probably came from those who've attempted to use these for more than 3 months at a time. If you really wanted sensitivity by a couple more orders of magnitude, you could go to liquid helium-cooled copper-germanium bolometers. So the key players here were really John Strong at Johns Hopkins, who started the whole field, and Alistair Gebbie's group at NPL. This is a lamellar grating instrument. I thought I had it. You can barely see the green spot on here, I'm afraid. But here, the path difference in the interferometer was generated by two interleaved mirrors here, one of which would move with respect to the other. And this was good for very, very far infrared measurements. By the time you got much above 100 reciprocal centimeters, then there was some parts of the physics which prevented you getting much better results than a standard Michelson interferometer. This was the instrument that was developed by Gebbie's group. Difficult to see exactly what it was, except for this very, very large beam splitter. This was about 10 inches across, and so you could get an idea of the size of this instrument. And this was very, very similar to the one that was commercialized by Research and Industrial Instruments Company. I was a graduate student at the time that they brought out the first one. In fact, at the time that they brought out the first prototype. And they put the first prototype in Harold Thompson's lab, and I was a grad student in Tommy's lab. And it had all sorts of problems. The moving mirror was a standard piston and cylinder with an oil bearing on there, and one little bit of grit would stop the motion for some time. And the output of the detector, what was actually the interference record rather than the interferogram, was put out on paper tape. And so you could, you could hear it, and its data rate was about 1 hertz. So you could hear ka-chunk, ka-chunk, ka-chunk all day. Except when the mirror stuck, in which case you could hear ka-chunk, ka-chunk, chunk, 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 chunk. And then you knew you had to start again. Tommy sent myself and my fellow graduate student Roger Lake down to NPL for a week, and this was one of the spectra that we measured during that time. So this was one of the very early instruments, the early spectra that were measured in it was actually in early 1965 when it was measured. And as I said, interferograms put out on punch paper tape, and then you had to take it to a remote computer facility and do the transform there. It was before the year that Cooley and Tukey reported on the fast Fourier transform algorithm. So even a 256-point interferogram, which is what this was taken from, took about 5 minutes to compute. The Golay detector was an interesting detector. Basically, what you had was the incident radiation coming in, which was chopped by a standard rotating mechanical chopper, hitting the a black mirror which was flexible and heated up this gas in the pneumatic chamber. And so the gas expanded and contracted as this mirror heated and cooled. And so the mirror deflected, and then the deflection of the mirror was measured here by this visible system here. So as the light beam from this light source over here, this white light source here, would pass through this grating, and when there was no signal, when the flexible mirror was flat, then the beam was blocked by this grating, and as the mirror flexed, then the light would pass to an increasing extent through here, and you would measure the signal at this detector. And that was the way that most of these instruments worked. Tommy held a conference on far-infrared spectrometry at Cowan College in Oxford in 1966. I apologize for the quality of this. This was scanned in from a photograph. But some of the players, there's more on here. This is this is Howard Thompson, Tommy Thompson himself. This is Alistair Gebbie and his sidekick George Chantry. I don't think there's anybody who was at this meeting here, right? Except me. And on the other side here, there were some of the greats of American spectroscopy, Dick Lord, Foyle Miller, who actually passed away this March at age 100, and Ellis Lippincott, who I ultimately postdoc for. This was my sidekick and roommate and lab mate, Roger Lake. And we were the gophers at this meeting. And so at one time, Tony came up to us and said, Lord and Lippincott would like to learn to play croquet. Go and teach them. So off we went and taught Dick Lord and others how to play croquet. And 1 year later, Roger was postdocing with Dick Lord and I was postdocing with Ellis Lippincott. It was the most productive game of croquet I ever had. This was just a photograph of the instruments in Tommy's lab. This was the NPL cube. This was the higher resolution in instruments here. This would get up to about 0.2 reciprocal centimeter resolution. This is actually measuring a heated gas cell here with the detector over here, and the drive was just a standard micrometer drive. Over here, not so easily seen, is the RIC FS520, and this whole big vacuum chamber here, the whole thing was evacuated, can just contain the interferometer. These were the control electronics here, and buried behind this curtain with the detect sampling and detection. This was actually a homemade far-infrared spectrometer that Tommy had made previously, which all the time that I was in his lab managed to get one spectrum during the time that we were using these other two instruments. It was still difficult to persuade Tommy that an instrument that worked without a grating or a prism could actually produce a spectrum. This was one of the spectra that I measured on that NPL cube instrument, and measured at 2/10 reciprocal centimeter resolution. This was actually the average of 9 scans, each of which took 6 hours. I was a cricketer at the time. This was perfect. I could come into the lab in the morning. I could set up the first scan of the instrument, pedal off to the sports field, play until tea time, dash back, reset the instrument for another 6-hour scan, celebrate the result with our opponents, replacing our precious bodily fluids. And after the pubs closed, then come back to the lab and reset it for an overnight scan. So 3 6-hour scans, 18 hours work at the I don't think I would have been able to be a graduate student and play cricket if it wasn't for that particular. Okay, enough of that sort of far-infrared spectroscopy. In France, Pierre Kahn's school was developing a very high-resolution instrument, better than 0.01 reciprocal centimeter resolution, and this was mainly used for near-infrared astronomical spectroscopy. So basically, the instrument was based on moving cat's eye retroreflectors. So you had a fixed cat's eye and a moving cat's eye here, and the optical path difference was generated by moving this cat's eye here. Why a cat's eye? Because any change in alignment was compensated by the optics of the cat's eye, somewhat similar to a cube corner in modern instruments, and so there was some just amazing results. They put out an atlas of planetary spectra measured with this instrument. Pierre Kahn visited Tommy's lab one time, and he brought with him a roll of paper, and he, in flamboyant fashion, took it and swept it across the floor so it opened up and you could see all the resolved lines on there. And it was about a little more than 10 times better resolution than anything that Tommy's lab was able to measure at the time. And he was a little shocked when Kahn said, "Oh yes, and this was measured with a source the intensity of Venus." This was never really commercialized. There were several instruments made in France by different people, but it was never the basis of a commercial instrument. The high resolution instruments were developed subsequently by companies like Bowman and Brucker, who used dynamic alignment of the moving mirror, and Brucker tended to use cube corners. But I wanted to put this in because the technology behind here, including things like gain switching to compensate for the variation in dynamic range of the interferogram, was developed because of this particular instrument. This again is a scanned in spectrum from that was published. Well, it was measured some time before. I took it out of the proceedings of a meeting in Aspen, Colorado, where incidentally, if anybody can get hold of those proceedings, they've got some remarkable tutorial lectures in there. I learned more about Fourier transform spectroscopy from the 8 tutorial lectures than anywhere else in my career. But you can see that basically you could go from relatively low resolution to higher resolution to higher resolution, and this top instrument was measured at 0.008 reciprocal centimeter resolution in the near infrared. The third sort of interferometer was really the one for which today's instruments are all based. These are the first of its type was a low resolution rapid scanning interferometer, a small one, which modulated where the beam was modulated without a chopper or without phase modulation, where you did the moving mirror, which was what was done in the near infrared. I forgot to mention. So as you move the mirror, the beam, the different wavelengths would go in and out of phase and generate the interferogram. This was a concept that was developed by a remarkable man called Larry Mertz, who worked for block engineering. This was one of these instruments. It was small, it was portable. Its beam splitter was about 1 centimeter across. Its drive here was a standard voice coil drive, typical of what's used today. The sort of drive that you'll find in the woofer of an amplifier now. And so as you increase the current through the coil, the Faraday's left or right hand rule drove the mirror through a magnet, and this was then the mirror moved back and forwards across here. This had only low resolution. It was about 16 reciprocal centimeters. For the mid-infrared, it used a standard thermistor bolometer. For the near-infrared, typically a lead selenide detector. As I said, it had a voice coil drive. The data was taken out onto digitized, taken onto a signal averager. And the signal averager was made by a company called Fabritech, who strangely enough became Nicolay. And Nicolay, of course, became Thermo Fisher, and so it goes. Once the interferogram had been signal averaged, it was played back into an audio frequency wave analyzer, and you could get and the output of the wave analyzer was the spectrum, and was output onto an XY recorder. So you didn't need a computer per se for this, and so you could get spectra immediately. And even though the spectra were low resolution, they were really high sensitivity. So the only work that was really done by chemical spectroscopists on this instrument was done by Manfred Lowe's group at New York University and Rutgers. And just to sort of give you an idea, this was the emission spectrum of aniline at a temperature of 30 degrees. So it was, and above it is just a transmission spectrum measured on the same instrument, to give you an idea of the sensitivity of this particular instrument. Block engineering put one of these instruments in Ellis Lippincott's lab when I was there, and they wanted to move the technology into the industrial and analytical labs. It was predominantly used by military. The whole thing was developed under military contract. One of the most interesting applications that somehow Block managed to persuade the military that it was feasible to distinguish between North Vietnamese and South Vietnamese by the emission spectrum of their face. It didn't work. But it led to the development of an instrument. It's an ill wind, as they say. So Lippincott came to me and said, "You're the only person in this group who's used an FTIR spectrometer. I was working on a non-spectroscopy project. After spending 3 years with the RISC FS520, I never wanted to see a Fourier transform spectrometer again in my life." Anyway, he put myself and a very talented grad student working on that part onto this, and we started playing in our quote spare time. One of the things we did was to interface it to a gas chromatograph, and we wrote it up and sent it to the powers that be at Block, and they said you can't publish it. Why can't we publish it? Because we're developing a higher resolution instrument, and your results are too good to show, and you'll show up the results of this new instrument. He then made one of the bigger mistakes of his life and offered me the position as product manager of the development of this instrument, which I took as a challenge. And if you can imagine a fresh off the freshly minted postdoc trying to run a group in chemistry, trying to run a group with no chemists, only physicists, electrical engineers, and computer programmers, it was a total disaster. So after about 3 months, I became product specialist and was able to actually use the instrument to do some measurements, and that was a much better use of my time, at least. So anyway, if you look at the interferometers in the 1960s, you'll see these names, especially John Strong, Pierre Kahn, his wife Janine Kahn. Pierre Kahn was the optics guy, and Janine Kahn was the computer guru. And Myron Block and Larry Mertz at Rock Engineering. And for those of you who didn't realize that, that was the origin of the title of the tour. I actually wrote this up 15 years ago after FTI had been going for about 40 years. And I figured that everybody would have forgotten about that one, so I could use the title. This was the new instrument. Actually, with the laser, it was laser reference. It was the first instrument with laser referencing. Had about a 2-inch mirrors, so about a 3-inch beam splitter. Germanium on KVR as the beam splitter. Very similar to the sorts of technology that's used today. The mirror was driven on a voice coil drive, and the signal from the laser interferogram, which was measured simultaneously with the IR interferogram, was used for several purposes. One, the zero crossings of the laser signal was used to trigger the analog to digital converter, but it was the sinusoidal signal laser interferogram was also fed back so that it was used to make sure that this mirror was being driven at a completely constant rate. Scan speed was constant to about 1/10%. So the instrument itself then was incorporated in optics, which looked like this. It was called the Digilab FTS-14. Digilab because the data system was supposedly part of a digital laboratory, which was also to be used for Fourier transform NMR, and also for what was then called television spectrometry, which is a shell-breaking optical emission spectrometer. So it was quite an ambitious development. The design of the optics was meant to replicate the design of a standard grating spectrometer at the time. So it had a side focus, which no instrument has now, and that was probably a mistake, but it was designed to take accessories that would fit into the standard grating spectrometers of the era. So you had basically an IR source, standard IR source, similar to what we use today. In fact, the first one was a nichrome wire source, but they very quickly went to Bobars. Through a resolution stop, sometimes known as Jacquinot stop, or J stop, where if you wanted to improve the resolution beyond 2 reciprocal centimeters, you had to stop the beam down to make it, the beam going through the interferometer more collimated. And so the collimated beam then was modulated by the interferometer, and then passed into the sampling optics. So, and here there was a flip mirror right here, which could direct the beam either through the sample and the reference channel, right here, similar to a double beam instrument. The only difference being that you did maybe 20 scans in one beam and then 20 in the other, and the idea was to compensate for any changes in atmospheric water vapor in the beam. There was a gun sight collimator right here, where because this was a germanium beam splitter that was invisible to the eye, that you could flip this mirror out of the out from its 45-degree position here, and this beam replicated this beam right here. So there was a focus at this point, and you could align accessories with that. This was actually a $10 World War II gun sight collimator from Abrams Optical, and when they ran out, there was nothing like it on the market. So in the end, they got rid of this component right here. So as you flip this mirror here, you of course flip this mirror here, and then the beam would go onto the detector, which in this case was a triglycine sulfate pyroelectric bolometer. The reason that you could no longer use a thermistor bolometer, which is actually more sensitive than the TGS detector, was that it wasn't fast enough. So the TGS detector can measure light which is modulated up to about 5 kilohertz reasonably well, and that was the laser frequency for the laser on the interferometer. So this was the first laser reference interferometer and the first use of a pyroelectric detector, and it was also very nearly the first use of a mini computer. There was a mini computer on here, and let me just show you what the data system looked like. So here we had the optics and the electronic controller of the spectrometer. Came out initially to a 14, then to a 15-bit analog to digital converter, and then it was signal averaged in a computer with an 8K memory. K, not M. Young people. The whole thing was controlled by a 256K disk. All the programs, all the data storage had to be put on this disk. The memory on the computer here was ferrite core semiconductor, and so you could see this great big. The memory board was about this big here, just with a whole bunch of little rings of ferrite core units on it. It was actually this was a 16-bit computer, and it was the first 16-bit mini computer. The mini computer that most people used at the time was a PDP-8, digital equipment PDP-8, which had a 12-bit word. And with a 15-bit or 14-bit analog to digital converter, you couldn't use the 12-bit word easily. So they went to a 16-bit, and Digilab were the first OEM customers of Data General who actually spun off from digital equipment to make this computer. The whole thing was controlled by an ASR33 teletype, a big clunky thing that stood off to the side of the instrument, and the spectral ultimately plotted onto a digital plotter with pre-printed chart paper because there wasn't room to put alphanumerics on the this computer. This is what I didn't have a slide of the earliest one, but this is what the first instrument looked like, except that it didn't have a CRT screen on here, and instead of this input device here, it had sitting side by the side this teletype. This is the digital plotter. The computer was in here, the disk was in here, and this was actually open area right here, which was a good thing for reasons that I'll tell you now. This instrument was actually first shown at the Ohio State Symposium on Molecular Spectroscopy in September of 1969. And it was shown, the conference started the day after a public holiday in the USA called Labor Day. Labor Day, all shops are closed. All technical shops anyway are closed. University had a holiday, Ohio State University had a holiday. But we were able to set the instrument up, and when we set it up, all of a sudden we saw in the spectra glitches every 200 reciprocal centimeters. And that told us right away that there was 60 hertz leaking into the system. And we realized that something that happened was different in Ohio than in Cambridge, Massachusetts, where the instrument was. In that we never saw that when it was set up in Cambridge. And the instrument had an AC power supply. And so we had to somehow get a DC source power supply, which had, what was it, 3.5 volts on it. All electronic shots were shut, including the one in the physics department at Ohio State. Fortunately, we brought along with us a first-year undergraduate, gopher, if you will, and a very, very bright kid by the name of Bruff Turner. And Bruff said, well, department stores are open. Why don't we buy a battery charger? And battery chargers you could be purchased at that time, which were 6 and 12 volts. Too high voltage for the source. So we bought a toaster. And we rewired the toaster to step it down the 6 volts down to 3.5. When this instrument was shown, sitting in this compartment here, hanging down here, was a toaster and a battery charger. And it worked like a charm. The next day, the conference opened, and people were very impressed, except for one thing. And that was the spectra were plotted from low wave number to high. What you might consider as the logical way, which I thought was the logical way to print out a spectrum. But infrared spectroscopists at that time, and still, tend to look at spectra from high wave number to low. It started off with prism spectrometers, which started off from short wavelength to long wavelength. When grating spectrometers came along with a linear wave number drive, they went from 4,000 to 400 or 200 reciprocal centimeters. And that's how people learn to interpret spectra, by this sort of visual pattern recognition. And so people looked at it and said, I really like the performance of that instrument, but I never buy one because the spectra come out the wrong way. Charlie Foskett, who was the manager of computing at Digilab at the time, had a cow and said, there's 2 months of programming to turn that around, because all the programming was done in machine code. And once again, Bruff Turner came through, and he said, well, instead of plotting spectra with the digital plotter going this way, why don't you plot it going this way? So all of a sudden, spectra were plotted from high wave number to low wave. Bruff went on. That's him. He went on to set up 2 companies and is a big player in the tech scene in Boston right now. And, you can see just how bright he was, what a problem solver he was by looking at his suggestions, which all these highly trained people were freaking out. The performance was pretty good. In fact, this happens to be a spectrum that I showed in a meeting in 1970, which was 2 superimposed spectra of polystyrene. And you can see the noise level is fairly low. Each was measured in a second, so it gave an indication that this was an instrument which was going to have an impact. What is not shown here is the fact that this is 3,400 reciprocal centimeters right here, and not shown is the region between 3,400 and 4,000. And the reason for that is because beam splitters at that time were single layer beam splitters of germanium on KBR, and the efficiency fell off dramatically as you got to, if the thickness of the germanium layer was optimized for 2,000 reciprocal centimeters, above 3,400 and below about 600 reciprocal centimeters, the efficiency of this beam splitter went haywire. So you would see, these are just single beam spectra, you could see how low the intensity was in that region. And if you look at a spectrum of polystyrene over the full range, it got pretty noisy. So subsequently, and it was some years after this, the beam splitters were made with multi-layers. In fact, today's beam splitters have about 19 different layers of dielectrics on there in order to get good performance over the whole mid-infrared region of the spectrum. This is just the efficiency of a single layer beam splitter, and you can see just how much the efficiency goes off as you go away from that center region right here. You can calculate theoretically what the performance of an instrument is. This is an equation which is in a book on FTI. I won't get into any great detail on it. But if you put the numbers on there, what you would expect is a theoretical signal-to-noise ratio should be about 8 times 10 to the 4th for 8 times 10 to the 4th for a 1 second scan. With all these others, this would be about a 1100 C source. 1100, there it is. This is the energy density, the Planck curve, if you will. This is the H1 the optical throughput, resolution, and the D-star of the typical TGS detector, assuming an overall efficiency of about 10%. And the detector area, which is 0.04 square centimeters, a 2 millimeter detector, which was used at the FTS-14 at the time. You look at today's instrument, the signal-to-noise ratio is significantly better than it's about. Today's instrument about 20 times better than the FTS-14, which is strange because a similar source is used. The detectors are a little bit better. They use deuterated alanine dope triglycine sulfate now, rather than just straight TGS. But the throughput on the FTS-14 was bigger. They used 2-inch mirrors, and today's instruments tend to use about 1. You used a 2 millimeter detector, and today's instruments use a 1 millimeter you would expect the performance of today's instruments to be worse. Where does it come from? Electronics. The electronics are so much better now that that you get really high performance on an instrument which is now so much smaller, more compact, more useful, cheaper than the old instruments. So Digilab started it all off, and then came a whole slew of companies, many of whom were taken over by other companies. Some of them were just when Buzz Beckman had a horrendous foray into FTL, and ultimately took it out of their product line completely. PerkinElmer dropped their hyphen. That's about the only period. But Digilab changed then, were taken over by Bio-Rad, who ultimately were taken over by private investors. Their spectrometer line and became Digilab again. And they sold that to Varian, and then Varian sold it to Hewlett-Packard, and Hewlett-Packard sold it to Agilent. It's a great allegory for American industry. So what I've tried to do is give you a rather personal view of the development of Fourier transform and Fourier spectrometry in the first real 10 years of its existence. I'd like to thank Mike for inviting me here and you for your attention.
I was going to say we're running late for lunch, but we're on time for the normal time. We have, after such a great lecture, time for a few questions. This is your chance to find out at the beginning of FTL. Any questions?
More of a statement, but I can assure you the Pierre Cone systems are still being used in NIST. Nice 6-inch retroreflectors are being used for IR measurements still. So
That doesn't surprise me at all. That's good to know.
it's a very solid system.
Oh yes, there's an amazing instrument.
Any more questions? If not, Peter will be here for lunch. We'll have plenty of time to talk over lunch. Let's all thank Peter again.